Hello, we are back. So this is one where we are doing algebra with abstract algebra, which I think is kind of cool. But so this one says, let A and B be an element of G, where G is a group. Show that A squared, A squared times B times X is equal to B, right? And show that it has a unique solution. Now, you might be saying, well, Professor Doyle, can't I just divide A squared by, A squared times B, right? And we'll have B over A squared times B, which will just be 1 over A squared. No, you can't have that, okay? You cannot have that. Why? Because this is a group, and we don't necessarily know if this is a group of real numbers. Division, as we know it, works with real numbers. But really what this is this is an arbitrary group, and we have to follow group arithmetic, okay? So, really, this is saying like A asterisk B asterisk X is equal to B, right? Where the asterisk is like some arbitrary operation, okay? I have like blue face right here. So, what we want to do is we want to show that. So we still want to solve for x, and then when we solve for it, we want to show that that solution is unique, okay? So the first thing we need to show is existence, okay? So existence. So showing that this exists. I kind of made that ugly right there, I'm sorry. Existence, okay? Okay, so we want to show existence of a solution. All right, so what we have is we have A squared asterisk B asterisk X is equal to B. Okay, let me give myself a little bit of room on this left-hand side. You'll see why in a second. Okay, so we are in a group. So we want to solve for X still. Okay, so I want to get this X by itself. How can I get that X by itself? Well, you want to operate with elements that get rid of A squared and this B. Well, lucky for us, we know that we are in a group, okay? So what does that mean? In being in a group, every element has a unique inverse, okay? So with A squared, what is the inverse of A squared? Well, with powers, okay, powers still work the same. If I have A squared and I operate with an A to the negative 2, right, that cancels out. It gives me my identity element. So here, I operate with A to the negative 2. But of course, what I do to one side, I have to do to the other side. Okay? So, that's how we do that. Now, what that implies for us is that I have A to the negative 2 operating with A squared, operate with B, operate with X is equal to A to the negative 2 operated with B. Okay? Now, A to the negative 2 times A squared, well, that is just the identity element E. So that is E times B times X equals A to the negative 2 times B. Well, what is E operating with B? E operating with B is just B. So this is just B operating with X equals A to the negative 2 operating with B. Now, what do you all think the strategy is now? We multiply by the negative B. Will be the negative 1, right? But we can't just do that on any side we wish because this is a group. It does not tell us that we are commutative, so we have to operate on the side that the B is on. So we have to multiply on this left-hand side, okay? So let me get back my blue. This is B to the negative 1 operating on B, which is operating on X, And so then what I do to one side, I have to do the other. That is b to the negative 1. And I'll just keep my same color palette here. Operate on a to the negative 2. Operate on b. And so from there, as you can see, that is e operating with x, which is b inverse, operate with a to the negative 2, operating with b. And of course, what that means is x is equal to b inverse, operate with a to the negative 2 times b. Awesome. So that's our answer, okay? That is our answer. We'll prove it in a second. We'll show it in a second. So, but what happens here is that we showed existence, okay? So now what we have to do is show uniqueness, okay? So it's not just enough to show that a solution exists. You have to show this is the only one, okay? So how do we show that this is the only one? Well, what we do is we think, okay, what if there was another solution here? Would it be the case that that one x would have to be equal to the other x, which equals that solution, okay? So what you want to do is you want to set up a dummy, okay? So to show uniqueness, let a squared bx equal to a squared bx prime. Okay? And what we want to do, we seek to show that x is equal to x prime. That's how you show uniqueness in abstract algebra, and in any real math class, actually. Sometimes this is done in advanced calculus and other courses of that nature. Okay? Hence, we operate by a to the negative 2 first, and then by b inverse to show. All right, so by doing that, we show that a to the negative 2 operate with a squared, operate with b times x. Let me just say operate with x is equal to a to the negative 2 operate with b equals a to the negative 2, operate with a squared, operate with b, operate with x. Notice how both of those are equal to b, right? Both of these are equal to b, so that's why we have this a squared, well, a to the negative 2 operate with b in the middle here. Okay? Well, then that obviously goes to e, right? So that's just, we can just say b times x equals yeah, b operated with x equals a squared operated with b, which is equal to b operated with x. Okay, so now from there, what we want to do is we want to get rid of this b on the left-hand side, which means we have to operate by a b inverse. Okay, so we have b inverse, operate with b, operate with x, and so for the middle, that's b inverse, operate with a squared, operate with b, and I'm sorry, I forgot the negative 2 right here. That's supposed to be a negative 2. So negative 2, operate with b, which equals b inverse, operate with b, operate with x. And so what that gives me is x, because remember, this all goes away. This is e, this is e. And so what I have is x is equal to b inverse, operate with a, to negative 2, operate with b, is equal to x prime. So this was supposed to be all primes, actually. Okay, that was the whole point. And what we just showed here, hence, x is equal to x prime. Therefore, unique. Okay, we have showed that these are unique. And there you go. Okay, that is the proof. So anytime you're asked to show algebra with abstract algebra, showing that some type of equation has a unique solution in a group, you have to show existence and uniqueness, and this is the process on how to do that. Thank you.